was recording the entire time. Abby, what about the fifth one?
-5.
Subtract 5 every time. -5, -5, -5. Works out. Jed,
Hi.
what's the last one?
Said square roots.
Square. I told you it was.
Other direction. Not square roots, but
Squares.
squares. You square the previous.
Roots.
Or just times it by itself.
Or just times it by itself. Okay. Beautiful, beautiful. So, getting into chapter 10, we are going to start talking about sequences and series. Sequences, the shortened version, is a list of numbers. Series is a list of numbers added together. So one of the key features of being able to do this is working with pattern recognition. That is going to be the main focus of today. Now, it's not just straight up recognizing the pattern, but actually recognizing some features of the pattern and how that relates to things we're going to continue to do throughout the chapter. Now, we're going to be writing a number of things in regards to these different sequences. So I'm going to come back to this page a lot. I'm going to move away from this page, and I'm going to come back to it a few different times because we're going to go through, talk about some definitions, talk about some things that lead us to know things about these patterns. And you're going to see me actually do this quite a bit in chapter 10 because the foundation of chapter 10 is all kind of built in things that in theory we already know how to do. So I will come back to that sheet. If you haven't already written a title, you should maybe have a title on your notes. 10.1 is called Sequences as Functions. First thing we're going to focus in on is what does it mean for something to be a sequence? Now, there is a technical definition and there is a nice, easy to understand definition. I already talked about the nice, easy to understand one. It is a list of numbers. With pattern. Now in mathematics, the pattern doesn't need to be any sort of complex shape or anything. It's just a pattern numerically. It's for a conversation from earlier if you missed that. Now that is the easy to understand definition. That's the Bensonism. But there is a more technical definition. And that more technical definition, we should talk about that too because that kind of builds the foundation of how we recognize aspects of these sequences. A sequence by definition is a function in which the domain consists of the natural numbers. And we're going to write something about that there in a second. I'm going to come back to that. And the range consists of real numbers. So, breaking this definition down to the key things that we are going to need to bring into what we are doing. First off, it is a function. That function piece takes care of the fact that these have patterns. By being a function, that means I can write some sort of equation related to how you get the terms. That equation will give us the pattern, in which the domain, is the domain the input or the output values? The input values consists of the natural numbers. What are the natural numbers?
The original number.
The original numbers. What are the original numbers? Good. Okay, let's be more specific.
The numbers that you started
The numbers that you started off
off with.
with. When you first learned numbers, what did you learn? 1, 2, 3, 4. It's the counting numbers. Natural numbers are the numbers that you find in the natural world. The numbers you find in the natural world are the counting numbers. Starting at 1. Yes? I was just about to get to that. 0 is not considered a natural number. In the natural world, when we initially created the world. I know, we created the world. It's a great new philosophy I'm coming up with. Anyway, when we started working with the idea of numbers, you never said you had 0 of something. No one ever did that. I have 0 apples in my hand. No, you just said you didn't have an apple. So 0 was something that was created much later than all the other numbers. It is not considered a part of the natural world because in nature, you just say you don't have it. You never actually quantify that I have 0 of it. Okay, so the domain, the input values are the counting numbers. 1, 2, 3, 4. Now, those domain numbers in a sequence are actually giving us the position of a number in a sequence. When I talk about these lists here, the domain is never outright listed out. But the domain is telling me on this first pattern, 5 is in the first position, 8's in the second position, 11's in the third, 14's in the fourth, then there's 5th, the 6th, the 7th, the 8th, and 9th. That location is where the domain is coming in. And the range, the output, that's what these numbers are essentially, is real numbers. What numbers are not real numbers?
Fractions and decimals.
Fractions and decimals are real.
Negative.
Negatives are real.
Is it the I?
Imaginary number?
Imaginary numbers. The opposite of real is imaginary. Imaginary numbers are not considered in part of a typical sequence. Are there such things as imaginary and complex? Complex numbers are the ones that include both a real part and an imaginary part.
Yeah.
There are such things as sequences and series. With those, we are not doing it. We are not square rooting any negatives here. We're sticking with real numbers. So, now, this tells us that when we're working with a sequence, that piece where it's said to be a function, we can write an equation, and at some point we will. Now, the equations that we're writing, they're not going to be in our typical old-fashioned function notation, the f of x, if you will, because there is a notation out there that is specifically designed for the situation of only natural numbers can go into the function. That notation is going to look like this. This notation here is kind of like f of n is equal to b. The A is kind of that function notation piece, just like the F is the function notation piece. The n is the number you put into it. In our sequence situation, that n is the position. And the b is the output. It's the number actually in the sequence. So to break this down a little bit. First off, this piece here. We say a sub n. That's how you say it, a sub n. If it was a number there, it'd be a sub whatever that number is. That a sub n is referring to the nth term or the equation itself is what it will be equal to. It will be equal to a specific number or it will be equal to that full equation. The n is technically referred to as the index. It's essentially the position. It's where our domain values go. Our 1, 2, 3, 4, etc. The B is the actual term. It's the number in the list. It's where our range values go. I already said this one. It's the numbers, the actual number in the sequence. That B, if it's a plain number as a number in a sequence, you could also put an equation in that location, which I already essentially stated. A sub n is equal to that equation. Now, when it comes to working with these patterns, one of the things that we're going to be focusing in on with these patterns, and I'm going to go back on this and I'm actually going to be writing some things here now. When it comes to working with these patterns, there's going to be a couple of things that we're going to have to focus in on. First off, the pattern itself. What is happening to get from one term to the next term? That's an important piece. That's not the only thing we have to do, because when it comes to these patterns, this first one, I know it's adding 3 every single time. But could I come to you and say, oh, the pattern is adding 3 every single time? Without giving you any other information, could you write out the entire list? Or any of the list? No. What are you missing? Where to start. The starting term in this notation, it's in the first position. It's known as a sub 1. So in this pattern here, a sub 1 is equal to 5, because that's the number in the first spot. It's our starting value. Now, if I tell you the pattern starts at 5 and adds 3 every time, could you start writing out the pattern then? Yes. A sub 1 in this one is 3. A sub 1 in this, 0.5. A sub 1, 81. A sub 1, 7. A sub 1, 2. So an important piece with working with these patterns is being able to identify that first term. But I'm going to tell you right now, sometimes that's not enough. The first one we already established. Well, let's talk about the second one here. The pattern is that you add the previous 2 terms. The first term is 3. Can you list the pattern? No. If I'm referring to the previous 2 terms, I need to know 2 starting values. Not only a sub 1, but a sub 2. Which is 5. On the third one, do I have enough information to say the entire pattern by just saying it multiplies by 2 and a sub 1 is 5.5? Yes. How about the fourth one? Fifth one? Sixth one? Square the previous, it starts at 2.
Oh yeah.
You started with 2. You square the previous to get the next one. 2 squared is 4. 4 squared is? Yes, that wasn't enough. It's only when it refers to going back multiple terms that you're going to need multiple starting places. Now, as we go through and do this, that recognition of patterns is not just going to go, tell me what the pattern does, tell me where it starts, and then I can write out the pattern. It's going to do a couple of other things too. We are going to do a couple of other things too. We are going to have to look a little closer at some of these patterns. I'm back on this page. Now, I'm not going to do this for every single one of the patterns, hence the reason, yes, this is the first pattern that we had on that sheet, but I'm just going to pull this one aside, and we're going to talk about this one a little bit. Now, we already established that a sub 1 is 5 on this pattern, and it shouldn't be much of a leap that a sub 2 is 8, a sub 3 is 11, a sub 4 is 14. What's a sub 5? 17. What's a sub 6? I heard 8, 21, and 20. 20, okay. Etc. So one of the things you are going to be expected to do is to be able to come up with the next numbers in the pattern. You don't have to write it this way. You literally could have gone up here and said 17, 20, and then kept going. I did this for a reason. And that's going to keep going. Eventually until you get to an nth term. An nth term, if you ever see a sub n, again, and I've said this before, and I have to say this like 20 times a trimester, I feel like sometimes, because it gets used in multiple ways. A sub n will show different things. Sometimes a sub n is going to be equal to an equation. And if I ever ask you to find a sub n, I am asking you to write an equation unless I'm specifying what n is. If I say find a sub n where n is 7, the other thing I could be looking for is a specific term. In that case, I was looking for the 7th term. So a sub n could also be a term in the sequence. But generally, if I give you a sub n, if it doesn't have a number down there, it's a term in the sequence in an unknown position. That's why it's n. Otherwise, if I know it's in the 5th spot, I'm going to write a sub 5. If I know it's in the 80th spot, I'm going to write a sub 80. Now, I wrote out these in this way because another thing, other than just being able to identify terms within the sequence and finding future terms that are not listed out, another thing you're going to be expected to do is to graph. Now, when it comes to graphing these sequences, there's a couple things you need to know. First off, you no longer have an XY axis. Because there's not an X or Y at all in sequences and series, really. Our values, our things that we get out of it are n's, which is our index. And I know that I wrote b as the range terms, but b is technically equal to a sub n, so this is the a sub n axis. So it's the n and the a sub n axis. Now, since n is of the natural numbers, you're never going to need the negative side of this axis. There is not a number in the negative 20th spot in a pattern. That doesn't make sense. So my n axis is always just going to be the counting numbers. 1, 2, 3, 4, 5, 6, 7, and that's as far as I can go for how I drew it. So those ones are always just counting numbers. My a sub n axis could be positive, could be negative, depends upon the pattern that you have. Is my pattern ever going to get negative numbers? No, so I didn't technically need this bottom part. Sometimes there will be negative numbers and you need it. And then this a sub n axis, I count that by whatever I need in order to get the points to fit. I'm going up to at least 20. So, I don't know. Counting by 2s is a little too small. Counting by 5s feels a little aggressive. I'm going to count by 4s. No specific reason did I choose 4. Other than, I want to get up to at least 20. Because that's where my numbers are. Here I'm just plotting a bunch of points. A sub 1 equals 5 has n value of 1, an a sub n value of 5. It's the coordinate point 1, 5. Move to the right 1 and move up 5. A sub 2 equals 8. Right 2 up to 8. A sub 3 is 11. A sub 4 is 14. A sub 5 is 17. A sub 6 is 20. Now I happen to have one more space, so I'm going to write my a sub 7 in there. I know it happens to be 23. Do not connect the points. I can't answer that question. I don't have an answer. Do not connect the points. If you were to go through and connect these points, what you are saying when you connect points on a graph is you are saying that those points are not the only thing in my function. You're saying anything in between them is also there. So you're telling me, if I were to look closely at like this point right here, you would be telling me that at the 2.5 number in the list, it's somewhere like around 10-ish in a list of numbers. Is there a 2.5 spot? No. Do not connect. Now, before I get rid of that though, in their connected form, what does it look like? This one looks like a line. It looks like a linear equation. That's because of what type of sequence this is. This is known as an arithmetic sequence. Arithmetic, spelt the exact same way as arithmetic. Why are they pronounced differently? I don't have an answer. An arithmetic sequence is one that when graphed, it looks like a disconnected line. It looks like a linear equation. What makes a sequence an arithmetic sequence is that you're adding the same number from term to term. Now, just a little comment on that. If I'm adding a negative number in the pattern, what does it actually look like I'm doing? Looks like I'm subtracting. Technically, when we talk about these arithmetic sequences, we are talking about adding the same number every time. But adding a negative looks like subtracting. So if you see a pattern that looks like subtracting the same number every time, it is arithmetic. Now that number that you're adding every time is known as the constant or common difference. And that common or constant difference is always depicted as D, the lowercase d. By the way, that common or constant difference also is equivalent to the slope of a linear equation. Going back to my other sheet. So, we established that this first one is arithmetic. If it is arithmetic, it has a common or a constant difference. In this case, that common or constant difference is 3, because the number you're adding every single time is that common or that constant difference. Is number 2 arithmetic? No. Is number 3 arithmetic? No. You're not adding or subtracting the same number. How about 4?
No.
How about 5?
Yes.
The constant difference, the number you're adding every time is? -5. Is 6 arithmetic? No. So arithmetic is one of the important types of sequences that we are going to be focusing in on this chapter. There is a second one. For the second one, we're going to look at, again, one of our patterns that we already had on there. 0.5, 1, 2, 4, 8. We are going to graph this one as well and look at what this one's graph looks like. In order to do that, I have to at least recognize a sub 1 is 0.5. A sub 2 is 1. A sub 3 is
2.
A sub 4 is A sub 5. Not that it has it on there, but what's A sub 6? 16, etc. I am going to emphasize this again. If I see A sub n, it is equal to either the equation or generally a term in an unknown position. Now, when you're graphing, you don't have to write this out every single time. I write this out because I'm essentially trying to practice the recognizing of that notation, because that's a huge thing throughout the chapter. These are not the x and y axis, they're the n and the a sub n axes. The n axis will never go negative. The a sub n could. This pattern doesn't go negative, so I didn't. My n-axis is always going to have those counting numbers, those natural numbers on it. My a sub n axis, I can go by whatever scale is necessary to get me to the numbers I need. I'm going to count by 4s again. Ooh, that wasn't quite enough. Yeah, it's okay. It'll do. Okay. A sub 1 equals 0.5. Talking about left, right, up, and down, where am I going to get to this point? Right 1, up a 0.5. Right 2, up 1. Right 3, up 2. Now the beginning of this pattern doesn't look like the scale is correct, does it? Looks like I didn't make it small enough. But these ones get bigger pretty darn fast once we start getting to it. And technically, not that I have room for it, but the next term is up here, and I'm going to do that because I need to show something. That's when n is 7. It's at 32. Do not connect the points. What does this graph look like? Increasing a lot. When it increases like this, starts with an E, looks like an exponential equation. If it looks like an exponential equation while graphed, is what's known as a geometric sequence. At least most of the time when it looks exponential. There is an exception. It looks exponential unless, and I'm going to leave the next line for me to write the rest of that sentence here in a minute. Now the pattern that happened in this one, this 0.5, 1, 2, 4, 8, etc., was when we were multiplying by the same number from term to term. This number we're multiplying by is called a constant or common ratio. It's given by the term R. Now, when multiplying by the same number every time, there's also the possibility of multiplying by a number that's between 0 and 1. And when you do that, the number gets smaller and actually doesn't look like you're multiplying by anything at all. It looks like you're doing the opposite, dividing. If it looks like you're dividing by the same number every time, technically you are multiplying by something, and it is a geometric sequence. Now, a geometric sequence generally will look like an exponential equation unless you have a negative R. This one was multiplying by 2. If it had been multiplying by negative 2, the graph would have not looked quite like we had it. It would have looked like this, where it was going up and down. It looks almost like two exponential equations diverging. Yes, you're not supposed to connect. I'm trying to show the U shape. So, it looks exponential unless R is negative. We already established that 1 was arithmetic, so it can't be geometric. Is 2 geometric? No. Is 3 geometric? What's r? 2. Is 4 geometric? What's r? It's 1/3. To divide by a third is to multiply, to divide by 3 is to multiply by 1/3, is to multiply by the reciprocal. Is this one geometric? No. In fact, when it comes to these terms, these two that are here, I'm just going to ask if they're arithmetic, geometric, or neither. You would essentially say they are neither. If you are curious, this one does have a name. It's a Fibonacci sequence. This one at the bottom, it probably has a name. Do I know it? No. If I was asked, is it arithmetic or geometric? I would write that it is neither. Same on this one, technically. You don't have to recognize that as a Fibonacci sequence. Fibonacci sequence is built out to where it's adding the previous two terms. That's what defines a Fibonacci sequence. Okay. So, the things you're going to be expected to do today. Identify a sequence as arithmetic or geometric. Come up with terms that come next in the sequence. Graph the sequence. Now, there's one quick thing I want to talk about that tends to mess with people. That I want to talk about, so I've got one more final example, but otherwise we're essentially done. Oh, the other thing you're going to have to do is find the constant difference or the constant ratio. Problems like this mess with people, though. When we look at patterns, you've been taught so much to focus in on the beginning of the pattern that we've lost some of the skills of looking on the later pattern, which is actually easier. To go from 6 to 4, I'm guessing most people would instinctually say -2. And then you'd look at the next one and say, that's not it. At least I hope so. When looking at these patterns, sometimes you're going to be better off looking at the fractions. Because we've been working with fractions for a while, so we should know that to go from a fraction to a fraction, clearly we're not adding or subtracting, otherwise it would be -2, -2, -2. The other option is we're multiplying by something. To figure out what we're multiplying by, fractions tend to be easier when it's not a nice number. Because how do you multiply fractions? Straight across the top. So when I'm looking for what I'm multiplying by, I'm going to ask, what did I multiply by 8 to get 16? What did I multiply by 3 to get 9? So what did I multiply overall? 2/3. So being able to look at those later ones can be easier than looking at the earlier ones. Now, granted, you can't assume that this is what's happening because it could be a situation where it's neither arithmetic nor geometric. But you can always go to a calculator and do 6 times 2/3 and see if you get 4. And you could do 4 times 2/3 and see if you get 8/3. So, this one is indeed multiplying by 2/3. And if it's multiplying by 2/3 every single time, the type of sequence it is geometric. And r is equal to 2/3. Now, another way you can find this, if you're like, I don't know what multiplies by 8 to get 16. I hope you do, but if it's bigger numbers that are less obvious. We generally work sequences from left to right. That's why it's multiplying. If I go the other direction, I am dividing. Pick 2 terms and divide them. I don't want to deal with those 2 if I don't have to. But I could have also said, well, I know that r would have to be whatever 4 divided by 6 is. And 4/6 as a simplified fraction is 2/3. So you can always work backwards and say the opposite of multiply is divide. this divided by this is r. And that would be true with any of these. I just really don't want to have to divide 16/9 by 8/3 unless I have to. Is it terrible? No. We know that to divide fractions, you flip the second one and multiply and you simplify. If I can skip that, I'm skipping that. Okay. So, that is it for today. Today's assignment is a book assignment. Now, before you go screaming that I am writing 2 through 50 evens, and I'm not joking, a lot of the questions are yes-no questions. You think you can handle some yes-no questions? And there's not 50 of them. Every other means there's half of that. A lot of them are like yes, no, or arithmetic, geometric, neither. So, it's a little bit longer, but that's because the pattern recognition is so important.